So in this lesson, we're going to talk about acid-base reactions. Acid-base reactions are also known as neutralization reactions because the acid and the base neutralize each other's properties to give you a salt and water. So this is an example of nitric acid combining with calcium hydroxide. It gives you calcium nitrate and water. Let's see in the next slide how this. Okay, so let us see how we have aqueous nitric acid and aqueous calcium hydroxide combined as an example of an acid-base neutralization reaction. So we write it as HNO3 aqueous plus calcium hydroxide. Okay, and this is also aqueous. And we do it like we've done precipitation reactions. The outside ones combine and the inside ones combine. So now we have H, OH. The H is from here. The OH is from here. The H is always got a positive 1 charge. It's also known as a proton or a hydronium ion. And the OH is a hydroxyl ion, and that's got a negative 1 charge from your polyatomic ions, remember? And so they just cancel out as HOH. The second one we want to write as calcium nitrate. So the inside ones go together. But remember, the metal goes before the non-metal. So we write calcium and then the nitrate. Remember, though, calcium is always positive 2 and nitrate is negative 1. So we need 2 nitrates for every 1 calcium to balance out the charge. This is aqueous, and this is water. You have to recognize that HOH is another way of writing H2O. But we write it like that because it's easier to balance, which is going to be our next step. So if we were going to balance, let's look at, we will look at the H and the OH as a group. So we have one H here, one H here. We have 2 hydroxyl groups on the left side. So and we only have 1 on the right side, so let us put a 2 right there. Okay? But now what have we done? We've offset the equation. Now we got 2 hydrogens, so let's write a 2 here. So there's 2 hydrogen ions, now 2 nitrates on the left side and 2 nitrates on the right side. Okay, and then we have 2 hydroxyls on the left side, 2 hydroxyls on the right side, and finally we only have 1 calcium, which is checked. So now our equation is balanced. So that's how we write our final equation. You can write this as H2O now. We just leave it in this form because it's easier to balance in this form. Okay, so you go ahead and you try this and then replay the video to see if you got the correct answer. Okay, so write a molecular equation for the reaction that occurs between aqueous. This is sulfuric acid, and this is potassium hydroxide. Now, we're going to recognize this as an acid-base reaction because this is got an H in it. It's sulfuric acid, and this has a hydroxyl group in it, and it's a base. So an acid and a base combine together to give us salt and water. So let's see how. H2SO4 aqueous combines with KOH aqueous, and then we end up doing the outside ones together and the inside ones together. Okay, so the outside ones will give us HOH. Another way to write water. and the inside ones give us K2SO4. Recall that the sulfate has got a -2 charge, so I need 2 potassiums because each potassium is a +1 charge in order to balance out the charge. So this is potassium sulfate now, and this is in the aqueous form. Now, the second step that we want to do is we want to balance our equation. Here we have 2 hydrogen ions. Here we have 1. So we need to put a 2 right there. Okay. Here we have now 1 sulfate, that's fine. And here we have 2 hydroxyl groups on the right side, so that means we need to put a 2 right here to balance the left side. Now we have 2 potassiums on the left side and 2 potassiums on the right side, so this looks all balanced. Let's rewrite it more neatly. And now I can just write it as H2O now that I've balanced it. And remember, I keep it in this form because it's easier to balance that way. And so that's our final equation. Do more example problems if you need. So we've talked about acid-base neutralization reactions, and sometimes we have compounds that undergo gas evolution reaction, like when we have sulfides reacting, the H2S is always evolved and it's a gas. Sometimes when we have anything reacting with carbonates or bicarbonates, our byproduct is carbonic acid, H2CO3, right? But that's very short-lived, and it breaks down automatically into carbon dioxide. You can see we can take a CO2 out of here, and what are we left with? H2O. So you'll get water and carbon dioxide gas. Same thing if you're reacting anything with sulfites or bisulfites. Your intermediate byproduct is going to be sulfurous acid, right? And then that will break down to give you SO2 gas, sulfur dioxide, and what's left is water from that. And ammonium also breaks down and gives you NH3 gas plus water. So, for example, if we have hydrochloric acid combined with potassium carbonate here, then we do our double displacement reaction here. The outside ones go together to give us H2CO3, which is carbonic acid. And the inside ones go together to give us KCl, which is our salt. Okay? The problem is this is very short-lived. Like we said, it's one of the ones that break down. So you have to be able to recognize when you see carbonic acid that it will break down to give you water and carbon dioxide. So this will break down once more, and then we'll still have our potassium chloride salt. Okay, so let's do an example. We have to write the molecular equation for the gas evolution reaction that occurs when you mix aqueous nitric acid with aqueous sodium carbonate. So remember that nitric acid comes from nitrate, which is NO3 -1 and has an H. The nitrate is -1, the H is +1, so we are good in terms of balancing charge. Now we need to add sodium carbonate. Remember, the carbonate is -2 and the sodium is +1, so that means I need 2 sodiums for every 1 carbonate to balance out the charge. Okay? Then we just do it like we've done before. It's like a double displacement reaction in which we swap ions, and we have H combining with the carbonate, but the carbonate has got 2 negative charge, so we need 2 hydrogens for every 1 carbonate. And then we have sodium combined with the nitrate. Sodium is +1, nitrate is -1, so we don't need to do any balancing. Next, we want to balance our equation. Don't forget to balance your equation. Here we have 1 H, here we have 2 H's, so let's put a 2 here. Now we have 2 H's on the left and 2 nitrates on the right, but we only have 1 nitrate on, 2 nitrates on the left, we only have 1 nitrate on the right. So let's put a 2 here. Now we have 2 sodiums on the left, 2 sodiums on the right, and 1 carbonate, or 1 CO3 on the left and 1 CO3 on the right. So it is all balanced. Next, what you want to observe is we just learned about gas evolution reactions, and we learned to recognize that H2CO3, or carbonic acid, is very short-lived. It's going to break down to give you what? Water and carbon dioxide. Okay? So let us rewrite the equation like so. And see how you would write this, and the carbon dioxide is a gas. For the most part, whenever you see water, just put the liquid state by it. Unless this is a very highly exothermic reaction, and so that will release a lot of heat. And so the water will actually come out as water vapor, but I don't expect you to know that. For now, just write water as a liquid state, and the carbon dioxide is in the gas state. Sorry, this is aqueous right there. And so we have a balanced final equation. Okay, go ahead and try doing this one, where you have aqueous hydrobromic acid combining with aqueous potassium sulfite. First, let's write out the reactants. And so we have hydrobromic acid combined with potassium. And remember, sulfite is like that. So potassium has always got a +1 charge, so it means we need 2 potassiums for every 1 sulfite. This is also aqueous. Now we're going to do what? The double displacement reaction, or the swap. The outside ones go together and the inside ones go together. So now the H combines with the sulfite, but sulfite again is -2 charge, so we need 2 hydrogens. SO3 aqueous, plus we have potassium combined with bromine, and potassium is +1, bromine is -1, so we don't need to do anything further. Next, what are we going to do? We're going to balance the equation. Here we have 2 hydrogens on the right, so let's put a 2 here. Now we have 2 hydrogens that are balanced. We have 2 bromines on the left, but only 1 bromine on the right. So let's put a 2 here. Now we've balanced the potassiums as well, because we have 2 potassiums on the right, 2 potassiums on the left, and 1 sulfite ion. Alright, let's remember one more thing about this. As soon as I see this, H2SO3, I'm going to recognize that it's going to break down and give me a gas. So we have water and a SO2 gas. You see, we take out an SO2 from here, and what's left over? H2O. Okay? This is gas, and again, you can put liquid water here. So let's rewrite this more neatly. 2HBr combines with K2SO3, and it gives us water and SO2 gas, and do more example problems if you need. Now we're going to talk about redox reactions, which is short for oxidation reduction reactions. And we've previously talked about precipitation reactions, acid-base reactions, in which ions were exchanged in solution. Here, redox reactions occur when we have a general electron exchange in a reaction. And one example of a redox reaction is the oxidation of something, in which we've seen before, in which you combust something. Anytime we say there's a combustion reaction, it means it reacted with oxygen gas. So when an element loses electrons, it's oxidized, and when the substance gains electrons in the reaction, it's reduced. And you cannot have one without the other. So in the reaction with solid magnesium and oxygen gas, you will have the magnesium ions are oxidized because anything in its normal state, so magnesium is found in the normal solid state, it would have an oxidation number of 0. Oxygen gas in its normal state has an oxidation number of 0, right? And then when they combine, what happens? The magnesium goes from 0 to a positive 2 charge, so it lost 2 electrons. When something loses electrons, it is oxidized over here. Okay, so it lost 2 electrons, and so it picked up a positive charge because electrons are negatively charged. So when you lose something negative, you become more positive. The oxygen atom, on the other hand, was reduced. It also had a 0 oxidation number in its normal form, and when it was bonded to magnesium, you see how it picked up a negative 2 charge, which means that it gained 2 electrons. So the oxygen atom became reduced, or it gained electrons. Okay? And this is how you remember it. Oil rig, oxidation is loss, reduction is gain. And this is referring to oxidation is loss of electrons, reduction is gain of electrons. So this is like that. So we saw that redox reaction occurs when something is reacted with oxygen, when a metal reacts with a nonmetal, and third, when you have just a general electron exchange. So which of these is a redox reaction, and explain why according to the rules that we've seen in the previous slide. When magnesium and oxygen combine, they form magnesium oxide. We already did this one, so that is definitely a redox reaction because of rule 3. We have a general electron exchange. This has an oxidation of 0. This has oxidation of 0. Here the magnesium must be positive 2, and here the oxygen must be negative 2. So the magnesium seems it lost electrons and became more positive. So according to oil rig, oxidation is lost, so this is oxidized. And here we go, the oxygen goes from 0 to negative 2. It means we gained electron, so reduction is gain. So this is reduced. So this is definitely a redox reaction. Number 2, it's not a combustion reaction. What it looks like is it's an acid-base reaction. So it is not a redox reaction. C, calcium plus chlorine gas gives us calcium chloride. Notice this is a metal and a nonmetal combining. This can also be according to rule 1 too, because it's a metal and a nonmetal also. But this is a metal and a nonmetal. Again, this is in its normal form, calcium in its solid form 0, chlorine in its aqueous form, or this would be actually gaseous form, is 0. Suddenly calcium, when it bonds, has a positive 2 charge, and the chlorine has a negative 1 charge. So you see the calcium gained or lost electron, so it's oxidized. It went from oxidation 0 to positive 2, so it means it lost electrons. And this chlorine was reduced. Okay, because it went from 0 to negative 1, so it gained electrons. So this is definitely a redox reaction. And then here we have, although zinc and iron are both non-metals, are both metals, we can see that there's an electron exchange. The zinc in its normal form, in its solid form, has an oxidation number of 0, and this applies to anything in its normal form as it exists in nature. That's what I mean by normal form, will have a 0 oxidation number. So when it picks up a positive 2 charge, what happens here? It lost electrons, so it's oxidized. Iron here, it was positive 2, and now it's iron in its normal form, which has a 0 oxidation state. So now it looks like it lost electrons. Sorry, it looks like it gained electrons because we went from positive 2 to 0. So that means this was reduced. Okay, now you go ahead and you give this a try and tell me which of these are redox reactions and tell me why. Is it because of 1, 2, or 3 in your previous slides? So here we have a metal and a non-metal combined in A, so it must be a redox reaction. Here we have electron exchange. We have the aluminum going from 0 to positive 3 and the tin going from positive 2 to 0. So that looks like an oxidation reduction according to rule 3. Here we do not have the rules that follow. It just looks like a regular double displacement reaction. So that is not going to be a redox reaction. And finally, D is anything that combusts with oxygen is going to be a redox reaction, because remember, a combustion reaction is a type of redox reaction. So that's that. So again, combustion reaction is a type of redox reaction. It's a reaction with oxygen gas to yield one or more oxygen-containing compounds. Combustion reactions are very exothermic, so they release a lot of energy. And this is precisely what happens when you have octane here. C8H18 is known as octane. When it combusts with oxygen gas inside your tank, your gas tank, this is what happens. You end up with carbon dioxide and water. Any combustion reaction, if it has C, H, and O, will end up giving you carbon dioxide and water. There is no ifs, ands, or buts about it, okay? But not all combustion reactions yield both water and carbon dioxide, since if you have carbon combined with oxygen gas, that's still a combustion reaction, but that only gives you carbon dioxide. How are you going to get water if you never had hydrogen? Okay, so you get the idea? Same thing with the second example here. You have hydrogen gas exploding with oxygen gas. Okay, great, we get water, but we don't get the other byproduct, carbon dioxide, because guess what? We don't have any carbon in our reactant. So, again, if you have carbon, hydrogen, and oxygen, you should always get carbon dioxide and water as your byproduct. In your gas tank, do we care about the carbon dioxide and the water? Is that what we're after? No, because we want energy. We only care about the energy that's released, the exothermic energy that's released. That energy is then what powers our car. We actually don't want carbon dioxide emissions, because I'm sure you've heard all sorts of issues with greenhouse gases. So that's how you know about combustion reactions. All right, let's do an example in which we balance it. We write a balanced equation for the combustion of liquid methyl alcohol. And I give you the formula for methyl alcohol. I don't expect you to know that. So CH3OH. Now you tell me you didn't give me anything else. Well, because I expect you to know that methanol here, or methyl alcohol, when I say combustion reaction, that means I have to explode it with some oxygen gas. Okay? And since it has carbon, hydrogen, and oxygen, what am I going to get? Carbon dioxide and water. Okay? So, let us balance this equation. It looks like I have one carbon here and one carbon here, so that's check. It looks like I have 4 hydrogens here and 2 here, so let me put a 2 right there to make that balanced. Okay. Then, finally, I have 3 oxygens here, and I have 4 oxygens here. So, how am I going to balance this? Because I have the oxygens in 2 different sections, or in 2 different compounds. So, here's what I will do. I think if I write 3 halves over here, you see how this cancel out, and I'm left with 3 oxygens. And then I have to add 1 more from here, so that is 4 oxygens. So that's balanced. But I can't have, erase this for a second, I can't have fractions in my balanced chemical equation. So the best thing to do would be then to take the whole thing and multiply it by 2. So now I have 2CH3OH, and then I have 3 oxygen gas multiplied by 2 carbon dioxide to give me 4 waters. Okay, and let me just double check that I didn't mess anything up. I have on the left side, let's see, carbons. I have 2 carbons here and 2 carbons here. I have 8 hydrogens here and 8 hydrogens here on the right side. And then I have, let's see, 1 and 7 oxygens here and, 8 oxygens here and 8 oxygens there. So it looks like it's all balanced out. And you see how the numbers here are in the simplest whole number ratio. I can't divide them any more than this, okay? So you have to make sure that the simplest whole number ratio. Okay, now you go ahead and you try, write a balanced chemical equation for the combustion of liquid pentane, a component of gasoline. And I give you the formula for that. Go ahead, try it first, then replay the video to see if you got the correct answer, okay? So, we have C5H12. And of course, since I said this is combustion, automatically you're going to know this. And is it going to yield carbon dioxide and water? Yes, because we have carbon, hydrogen, and oxygen. We have all our components. CO2 gas plus. And the water, if you're curious about this, since it's highly exothermic, it's probably going to be in the gas phase, but if you put in the liquid phase, that's okay. Liquid or gas is fine. This is highly exothermic, so it releases a lot of energy. So it's probably going to be in the gas phase. But I won't count you off on that, okay? The most important thing is you put carbon dioxide and water. Then let's go ahead and balance, okay? We have 5 carbons here and 1 carbon on the right side. So let us put a 5 so that balances out. Here we have 12 oxygens. Here we have 2. So let us put a 6 right there, okay? To balance that out. Now we have 2 oxygens on the left. Let's count how many oxygens on the right. 10 oxygens here and 12 oxygens there. or sorry, 6 oxygens here. Okay, so that gives us 16 oxygen on the right. All right, now this one is easier than the previous one because we only have the oxygen coming from the oxygen gas. So this is simple, and we have to put an 8 here because 8 times 2 is 16 oxygens. Now this is all balanced out. Let's just double check, okay? On the left we have 5 carbons. On the right we have 5 carbons. On the left we have 12 hydrogens. On the right we have 12 hydrogens. On the left we have 16 oxygens, 8 times 2. And then here we have 16 oxygens. 10 oxygen from carbon dioxide and 6 from water. And so this is balanced.